and D2A. D2A is just linear operation, easy peasy. The D2A, A to D is hard. So what we do for A to D is actually a search. So we search for the D because there is no way to actually start from the analog and directly go to D. You would say, let me see, this is A, I guess the D is 0. And you test it, oh no, it's too low. You increase your guess, and you increase your guess until you reach it. That would be the simple way that you just count up until you reach. But we don't do that. That takes too long, and it's not efficient. Instead, we use binary search. So let's do an example. Let's say that n is equal to 3, and your Vref minus is 0, and your Vref plus is 14 volts. So the first thing I want to say is that what is digital resolution? Say it again. 3. What is analog resolution or LSP voltage? What is it? Which is 7, which is 2. It's not accidental. I chose it such that it comes out like this because it makes, for you, starting doing this example makes things easy to see. Now, did any of you go and use these Octave programs I shared with you, or MATLAB? I don't know if you, do you all get MATLAB as part of your package when you enter school? So you have, I should ask to get one. So I want to use this one. So this one, if whenever you like to be looking at any conversion and you wonder how it looks, I don't have a real MATLAB, so for me, I cannot go to big ends, but I can easily do small ends. And this shows the D to A conversion. This shows the A to D conversion. So let me copy this image. Is there any way that I guess I have to download it. Okay. Insert. No. So this shows what we just, the example we created. Now, very easy. Let's say that I want to convert this value, no, not that value. Let's say that I want to convert this value, which is 10.25, this is 10, this is 11, this is 10 and a half. So if my V analog is 10 and a half, then what is my digital value? Well, all you have to do, look at here. What is it? 5. That's using the table. But of course, you don't have a table. The N are big, and it doesn't make any sense to use a table. And there are a lot better ways and good ways to do it. So why use a table? So instead, we use SAR, which is basically a binary search. And the way it is that if N is equal to 3, then I have 3 rounds of guessing. So always you have the same number of guesses as the number that N you have. So it makes it very easy. You go and you say, okay, In binary search, what is your first guess always? The middle value. So for us, you're gonna say, when you have n equal to 3, then you have 0 to 7 as your options, and the middle one is what is 4. So you start from the middle. This would be my first guess, 4. And when I go with my first guess, then I turn it into voltage, because look at up here. You go, this is important. This is like your guessing machine, if you think about it that way. Then it goes through a digital to analog converter. When it goes through that, it gets an analog guess that compares it to the Vin. So over here, I get an 8. And so let me put it round. This is my round number. And the guess, what was our guess? Digital, I call it the digital guess. It's 4. What would be the analog equivalent of the guess? That's the one that we came back and got an 8. It's 8, right? And then you say, is Vin more than my analog guess? More than or equal? And the answer is yes or no. Because my Vin, remember, is 10.5. This is my Vin. Is it more than it or less than it? It is more than. So it is yes. If that is yes, what does it tell you about the digital value of Vin? Whenever we get to the final answer, we just compare it to one number only, but it gives us a definite answer about one certain thing about that digital value. What is that certain thing? It's the MSP. Now we know the MSP is 1 because it is more than just like the thing that is in the middle, and the MSP is 1. This number is bigger than that, so for sure the MSP is 1 in it. You can't have an MSP that is not 1. And therefore, you have your, for this one, I say the bit is 1. The bit you make a decision about is always the MSP plus 1 minus round. Like we can change this to round 0 and then it becomes easy. So whatever round that you are looking at the bit that you are making a decision is the MSP minus round. For us, round is 0, so we are making a decision on bit MSP. What is the second guess? It's a binary search, so I'm not telling you. You tell me. What is the second guess? The digital guess. No, we have a digital. We are not making analog guesses. What is it? 6. So this was my first guess. This is my second guess. And the second guess, we have round 1. Digital guess is 6. Analog guess is what? 12. Is Vn more than or is it Vn more than the analog guess? Yes or no? No. What can we say about that bit? It's 0. And what bit was it that we just made a decision about? It was, sorry, MSP minus round. So this one was MSP. This one was MSP minus 1. The bit that I'm looking, the index of the bit. The next step. What comes after 6? What is the third guess I have to make? 5. So I choose this one. And my analog guess is gonna be 10. So that is, oops, 5. Analog guess is 10. Is V in more than the analog guess? Yes or no? Yes. And the bit value is 1. And for us, because we had only 3 bits, this is bit 2, this is bit 1, and this is bit 0, which is your LSB. So what is the answer to this question? It's 101. What is 101 in number? It is what? 5. Did we guess it right or not? Yes, we did. This is happy ending. If you do this for a different number, you will get a not very happy ending. I don't want to go over the details of it in class, but I tell you, and if you are curious, you will do it and you will see for yourself. It's very easy. For any, you see, this is the middle of the step, right? Everybody look at me because you may get curious later. This is the middle of the step. For all the numbers, analog numbers that are on the left side of this algorithm gives happy ending, like the one we just saw. For everyone on this side, you will get 1 LSB error, just 1 LSB, not more than that. For big ends, that 1 LSB error is very little, so it doesn't matter. However, let's say that your n is equal to 6, and the value you get could be 1, 2, 3, 4, 5, 6. So this is the correct value, but you get this. We call so this, how much error is this in this? 1. But the Hamming distance is huge. Do you know what's Hamming distance? Hamming distance is the number of bits that are different. How many bits are different? All 6 of them. So the Hamming distance is 6. It looks very wrong, but it's only 1 LSB different. Why does this happen? Because when we are making the comparison, we are making this comparison with the analog guess that is right in the middle. For these that are on this side, they actually should have been considered a 1 for that answer, but they get a no for that answer. And that's why that happens. But you don't need to worry about it. And whenever you get a question either in the exam or you're for homework, regardless of what part of this step it falls, you follow the same algorithm I just gave you. And if you do a mathematical operation yourself and you see that, oh, this number doesn't match that, so maybe I made a mistake. No, maybe you didn't make a mistake. This is just an inherent error built in this algorithm. Yeah? So don't panic, but know that this exists. So if I want to summarize it for VIs that are more than or equal middle of the step, error is 0. For others, error is 1 LSB. So you just have one wrong value. You're wrong by 1 bit. So that's the end of our class, right? So which means good. I didn't get to talk about anything that the students may miss. This was just a review. Oops. Thank you for listening. Let's stop this. I don't know how to stop it.